Continuing on our theme of acid-base chemistry, today we start buffers. A buffer is a solution that will resist changes in pH when small amounts of an acid or a base are added to the solution. Notice it says it resists changing pH. Doesn't mean the pH won't change just a little, but there won't be any wild swings in pH. Now, this is important for systems that operate under a specific pH concentration. Your blood is buffered, okay? Your blood wants to maintain a pH somewhere between 7.25 and 7.45. If your blood pH gets out of that range, your body starts to do funky things, okay? There's a different buffer that's operating inside your cells, and there's a third buffer that operates in your kidneys. So there are lots of systems where maintaining the pH, the hydronium ion concentration in solution is important. So if I added a bit of acid to a beaker of plain water, the pH would plummet dramatically. If we added the same amount of acid to a buffered beaker, a beaker that was made up of a buffer solution, the pH would barely change. Now, I would normally do that, but we're working in virtual world here. Okay. The key to a buffer solution is the fact that it's a two-component solution. It's a weak acid and a salt that contains its conjugate base, or it's a weak base and a salt that contains its conjugate acid. The secret here is that you've got large quantities, relatively speaking, of a weak acid and its conjugate base, or a weak base and its conjugate acid. So if I had HF and a sodium fluoride, I'd put both of those in solution so that I've a substantial concentration of HF to begin with and a substantial concentration of fluoride ions to begin with. I've got a buffer. Ammonia and ammonium chloride. Acetic acid and sodium acetate. Okay, when we did one of our experiments this semester, we had an acetic acid buffer. One of the solutions we used was an acetic acid buffer. Okay, so any combination of weak acid and a salt containing its conjugate base, or a weak base and a salt containing its conjugate acid, can be used to create a buffer. Let's do some calculations looking at adding a small amount of acid to a pure water solution, and then the same situation for a buffer solution. So, pH of absolutely pure water is 7. Okay? Now let's add some HCl to a concentration of 0.010 molar. If we do that, the pH drops from 7 to 2. That's a 5 pH unit drop. That's major. So this very small addition of HCl produces a large swing in pH. Now let's think about having an HF sodium fluoride buffer. Okay? So let's start out with a 0.1 molar HF solution, 0.1 molar sodium fluoride solution. There's our reaction. Ka is 6.8 times 10 to the minus 4, my ice chart. Okay? 0.1 for HF, 0 for hydronium ions, 0.1 for fluoride ions, so it's minus X plus X plus X. So 0.1 minus X, X, and 0.1 plus X. There's my Ka expression. I'm going to assume that X is going to be much, much smaller than 0.10. If I do that and I plug into my Ka expression, I get 6.8 times 10 to the minus 4 is X times 0.10 over 0.10, and I get X to be 6.8 times 10 to the minus 4. Our hydronium ion concentration is equal to X, So X is equal to hydronium ion concentration is equal to 6.8 times 10 to the minus 4. Our pH is 3.16. Okay, so that's what the pH of this buffer solution starts out at. Now we're going to add the HCl to this. If I add a little HCl to the buffer solution, and it's got a concentration of 0.010, then my initial concentration of fluoride ion is not going to be the 0.1 initially, but it's going to be 0.10 minus 0.010. That's a strong acid. I added it to this acid-base reaction, okay, that's in a buffer solution. It's going to eat up some of the weak base. It's going to make some of the conjugate acid. So that's going to go to 0.90, and this is going to go to 0.11. So I've got a new ice chart, 0.110 and 0.09. Still minus x plus x plus x, so I have 0.11 minus x, and 0.09 plus x. I'm going to assume that x is going to be much, much less than 0.09. I mean, our Ka is times 10 to the minus 8. I think we're perfect. No, times 10 to the minus 4. We should be good. Okay? So if we solve this for x, 6.8 times 10 to the minus 4 is equal to x times 0.090 over 0.11. I get the hydronium ion concentration to be 8.11 times 10 to the minus 4. pH of 3.08. So the pH went from 3.16 to 3.08. That's very little change. It's not the 5 pH unit change we saw when we added the same amount of acid to straight water. So the addition of an acid lowered the pH a little, but not much. Now, the reason a buffer solution does what it does is because of the common ion effect. The solution contains an acid and a salt that contains a conjugate base that is common with the anion produced by the acid when it ionizes in water. The common ion. And this interferes with the forward progress of the reaction. You've already got some product in there, why make more of it? And so that means that you keep a substantial amount of weak acid and conjugate weak base in solution, and it controls how much hydronium ion is produced. So we can do problem 17.1 on page 743. Okay, 743. All right, now let's look at the problem and then we'll work it. Okay, there we go. It says calculate the pH of a buffer solution that contains 0.200 molar acetic acid and 0.100 molar sodium acetate. So we have 0.200 molar acetic acid and 0.100 molar sodium acetate. Now, since we're dealing with acetic acid, I need to look up the Ka for acetic acid. And the Ka for acetic acid is Ka 1.8 times 10 to the minus 5. All right, so let's work. Now, I have CH3COOH reacting with water, liquid, aqueous, going to H3O plus, aqueous, plus CH3COO minus aqueous. Okay? And that gives me an ice chart that looks like this. CH3COOH, H3O plus, CH3COO minus. This is 0.200, this is 0.100. It's going to be minus X plus X plus X. So 0.200 minus X, 0.100 plus X. If we write our Ka expression, it's going to be hydronium ion concentration times CH3COO minus concentration all over CH3COOH concentration. Now, look at the size of Ka. I'm going to assume that it's less than, X is going to be less than 0.1. So I'm going to go 1.8 times 10 to the minus 5 is equal to X, 0.100 over 0.200. And I assumed that X is going to be much, much less than 0.100. 1.8 EXP5 negative times 0.2 divided by 0.1. I get X here to be 3.6 times 10 to the minus 5. That was definitely a valid assumption. Okay? So, that means that my pH is going to be the negative log of 3.6 times 10 to the minus 5. So the pH here is 4.44. Okay? Now, you guys can try practice problem 17.1, the more practice, if you want. Okay? Or do your homework, either way. Now, let's take and think about solutions. Okay? Usually when we disturb a solution, we do it by adding a volume of some kind of acid, let's say, to a already mixed solution. So let's say I added 2 milliliters of 0.100 molar HCl to 20 milliliters of a 0.10 molar HF, 0.10 molar NaF solution. And let's think about what happens. Now, when I add 2 milliliters of the HCl, first thing off the bat we ought to realize is the volume of our solution changes. I no longer have a 20 milliliter solution, I now have a 22 milliliter solution. So we have to think about the moment right after the disturbance. Okay, if we think about the moment after the disturbance, the concentration of HF at the moment the disturbance has happened is going to be the molarity of HF times the volume of the solution plus the molarity of the HCl plus the volume of the HCl added, because HCl is going to eat up the conjugate weak base and make the weak acid, divided by the volume of the buffer plus the volume of HCl added. The concentration of the fluoride ion is going to be fluoride ion concentration times the volume initially of the buffer solution minus concentration of HCl times the volume of the HCl solution divided by the buffer plus the volume of the HCl added. So when I do that, 0.1 times 20 plus 1 times 0.2 divided by 22 should give me 0.10. 0.1 times 20 minus 0.2 times 1 equals, divided by 22. Why did I put 1 there? I have a typo. should be 2 because we added in 2 milliliters. So guys, right here, that should be a 2. That should be a 2. That looks better. Let me check the math. Make sure that I didn't make that mistake when I was calculating. So 0.2 times 2 plus 0.1 times 20 divided by 22. I should go 0.11 here. And 0.2 times 2 negative plus 0.1 times 20 divided by 22. Okay, that actually changes that to 0.073. All right. Now, so if I come in here, this is going to be 0.11. And this is going to be 0.073. So I have 0.11 and then it's 0.073. That. Okay, I'm going to assume that x is less than 0.073. So when I do that, hold on. When I do that, what we're going to get is I skipped something. We did that. Okay, guys, I skipped something. I'm sorry. I ran way down. Before I finish this out, this is where we are. Right here. Okay? So, let's talk about something called the Henderson-Hasselbalch equation. Because we almost always, 99.99% of the time, are going to make this assumption, we are going to use something called the Henderson-Hasselbalch equation that is based on that assumption. In the Henderson-Hasselbalch equation, pH equals pKa plus the log of base divided by acid. Now, I can derive this equation for you. You can see it derived in the book, but I'm pretty sure you don't care. So I'm going to copy this, take it down here, and we're going to paste it. Okay? So if I use this equation, the base concentration is going to be 0.073. The acid concentration is going to be 0.110. And there's the pKa for our acid. So 0.073 divided by 0.110, take the log of that and add it to 3.17. I get a pH here of 2.99. It started out in our pure solution at 3.17. We went to 2.99. That is not much of a change in pH. The pH shifted a little bit, but not dramatically. Okay? Now, I'm going to jump back up here, because I was a bad girl, and rolled the thing down too much. Let's just look at a simple Henderson-Hasselbalch problem 17.2. It says calculate the pH of a buffer solution when 0.250 molar HCl and 0.170 molar KCN solution is made. So in this solution, we're given HCN and KCN solution, and the concentration here is 0.250 molar, and the concentration here of the KCN is given to us as 0.170 molar. The Ka for our acid is 4.9 times 10 to the minus 10. Now, we need pKa. It's a negative log, 4.9 times 10 to the minus 10. So that's 9.31. Okay? So pH here is going to be 9.31 plus the log of our base concentration, 0.170, or our acid, 0.250. 0.170 divided by 0.250. Take the log of that. So I get 3.91 minus 0.167. No, plus a minus 0.167. So I have a pH of 9.14. So this solution should have a pH of 9.14. I should expect it to be less than the pKa because I have a higher acid concentration than base concentration. Okay? So, buffer solutions. When we're dealing with buffer solutions, we're always going to use the Henderson-Hasselbalch equation. pH equals pKa plus the log of base concentration over acid. Okay? Now, I did the one where we did the disturbance for you already. I did them out of order. I apologize. So let's scroll on down here. Let's talk about buffer capacity. Buffer capacity is a measure of the ability of a buffer solution to resist changes in pH. The buffer capacity depends on the concentration of the weak acid and the weak base in solution. The higher the concentration of each component, the higher the buffer capacity. Now, your buffer capacity, you're going to build your solution to handle the kind of disturbances you want to deal with. So if you know that your solution is going to have to take a lot of abuse, you want your concentration of the components to be high. If you know it's not going to have to deal with very large disturbances, you would build your buffer so that your buffer capacity is low. Now, it also depends on their relative amounts. The more equal their concentrations are, the better your buffer capacity is, the better your ability to handle an acid disturbance and a base disturbance. The buffer range is a range of pHs over which you can use an acid conjugate pair to produce a buffer. It's always plus or minus 1 pH range from the pKa. The closer the pKa is to the pH you want to maintain, the better your buffer is going to be able to buffer. Okay? Notice that 1 pH unit means that there's a 10-fold difference in concentration. You get any more than a 10-fold difference in concentration, it's really hard to deal with. Okay? The solution is not going to be very good at buffering. Now let me look at this conceptual question and see if we want to do it. Nah, I'm not real fond of it. Now, I think this is a good place for me to stop because the next thing we're going to talk about is titration, and I want to do titration as its own kind of unit. So this is where we'll stop. We'll pick up here next time.